Hello everybody. So now let us continue our discussion from where we left in the last lecture. In the last lecture we were talking about the hydrophobic effect. And we also talked about the importance of solvents and their role in forming solute-solvent interactions, and also during the process of crystallization these solvents play a very important role, and there are hydrogen bonds as well as dispersive interactions depending upon the nature of the solvent and the solute. Now the process of solvation, the dynamics associated with solvation is extremely important in host gas chemistry. Dynamics of solvation are extremely important in host gas chemistry. Why? Because the thermodynamic and kinetic considerations are extremely important. And primarily we are looking at a host plus a gas in the presence of a solvent to form the host gas complex, which is solvated. And it is important to understand the role of enthalpic and entropic contributions that govern host gas recognition. So to start with, let us look at the different processes which are involved during the process of complexation of a host and a guest in the presence of a solvent. So to start with, we can now consider a three-dimensional host. So this is a three-dimensional host, and this host to start with has been dissolved in a particular solvent. So the host is solvated, the guest is also solvated, and we'll now look at the processes which takes place on thermodynamic grounds when a host complexes with a guest to form a host gas complex. So to start with, this is highly solvated by polar molecules of the solvent, or these are the solvent molecules you can consider. In general, you can consider this is a solvent in which I have dissolved my host, and all kinds of interactions are present here. We have already discussed you can have hydrogen bonds plus van der Waals interactions which are present. Now if a host has to complex with a guest, the first process is the desolvation process. During the process of desolvation, now I would represent this 3D host in a slightly simplified way just for the sake of discussion. So I am considering this to be my 3D host now, and the desolvation has happened and the solvent molecules are now released away. So when you have the desolvation of the host, this is enthalpically unfavorable but entropically it is favorable. This is because when you remove the solvent molecules, then you eliminate the hydrogen bonds which stabilize the host. So, enthalpically unfavorable, but entropically you increase the number of particles in the bulk. So, this is an entropically favorable process. As we have already realized that the host must now get pre-organized because it is a conformationally flexible host. Therefore, now there has to be a change in the conformation, and the host now rearranges into a different conformation or the more active conformation before it will encapsulate the guest. So, now you see here that there is a conformational rearrangement. There is a conformational rearrangement, and this conformational rearrangement is both enthalpically and entropically unfavorable. Why? Because energy has to be spent by the system in trying to change the conformation, get it into the more active conformation, and it is also entropically unfavorable because now you are going to restrict the motion of the conformationally flexible molecule. So, there is a conformational restriction, so the entropy loss takes place, and there is an enthalpy contribution because energy is necessary to change the conformation. And it is at this stage that we discussed that if you have a pre-organized host, then the process is highly facile because this enthalpy and entropy cost will not be involved. Already during the process of synthesis, this cost would have been paid during the process of preparation of the particular pre-organized host, and therefore that will not play an important role now. So, however, now that we have got a pre-organized host, so this is the first stage where you have the host being solvated, the second stage which is the desolvation, the third is the conformational change. So, these are the processes which happen from the host side. Now, coming to the guest side, you have the guest which is actually solvated. So, this is the solvated guest. For example, we have the different coordination complexes, and now we have the desolvation of guest, because if the guest has to coordinate with the host, then it has to remove the solvent molecules, the solvent shell has to be removed. So, we now get the isolated guest and the solvent molecules are in the bulk. In the next stage, we now have the complexation process where the host and the guest complex with each other. So, now the host and the guest are going to complex with each other, and this is going to be the sixth stage. So, the fifth step is here, the desolvation of the guest. Now, desolvation of the guest again is like the desolvation of the host, is enthalpically unfavored and entropically favorable. Now, we have the complexation between the between the host and the guest to get the host guest complex has been now formed, and so this process is enthalpically favorable because there are enhanced host guest interactions, there are host guest interactions. And then we have got the next stage where we have the solvation of host guest complex. This will give you now this is the solvation of the complex, and this is enthalpically favorable, but entropically unfavorable, because the solvent molecules which were present in the bulk will now come and coordinate with the host gas complex. And overall, now at the end of the process, we see that after we have considered the desolvation and we have considered the solvation processes, we have seen now that the solvation of the host gas complex takes place. So effectively we see now that at the end of all these processes, this amount of solvent is still released into the bulk, and therefore this results in favorable increase in entropy. So overall we see that the process of complexation of the host and the gas releases solvent molecules into the bulk, and therefore that increases the translational entropy of the system, and therefore we say that host gas complexation is favored by an increase in entropy of the system. Enthalpically also it is favored, because now the host gas complex is stabilized by favorable interactions between the solvent and the host gas complex. So overall the host gas complexation dynamics are such that you have a stabilized species where desolvation processes are involved, this conformational change which is very important, and then you have the host gas complexation followed by solvation of the host gas complex to form the final state of the complex. So all these processes operate, and that is the reason why solvation is a very important effect. And we can take one particular example just to illustrate this particular effect. For example, we will see now that say you have got a non-polar molecule, or you have got a organic molecule which has got polar plus non-polar parts, polar plus non-polar parts. Let us consider, for example, cyclodextrin, which has got some polar heads and it is solvated. So there are water molecules which solvate the cyclodextrin, and now you add a guest. So what will happen is that the guest molecules will now interact with the cyclodextrin, and it will form favorable host gas interactions, and the water molecules will be released, into the bulk. Now to start with, the water molecules which are interacting with the cyclodextrin cavity are not in a very stable configuration. Why? Because they are interacting partly with the polar functional groups, but they are also interacting with the non-polar functional groups, and we know that these are hydrophobic surfaces, and water is a hydrophilic solvent. So there is a repulsion between the hydrophobic and the hydrophilic parts, and therefore the water which is interacting with the cyclodextrin cavity are considered to be high energy water molecules. They are considered to be high energy water molecules, and these high energy water molecules now what happens to them, that when the guest now goes and complexes with the cyclodextrin, these high energy water molecules are now released into the bulk, and there they are in a much more stable environment because they form extensive hydrogen bonding with themselves. So, hydrogen bonding between the water molecules in the bulk stabilizes these water molecules, and the guest also gets stabilized because of the favorable hydrophobic interactions, because the guest can have hydrophobic parts which is interacting with the hydrophobic parts of the cyclodextrin cavity, and therefore the guest also gets stabilized in the host cavity. So, and we see that that enthalpically this is the favorable process because you have enhanced host guest interactions and you also have hydrogen bonding between the water molecules, and entropically also this is a favored process because the water molecules which were having a very ordered arrangement around the cyclodextrin cavity now get released into the bulk. Now, when they get released into the bulk, that increases the entropy change for the process, similar to what we have observed in the previous case, that the water molecules which are released overall increase the entropy of the system. Here also the water molecules which were initially solvating the cyclodextrin cavity and which were in a relatively high energy arrangement now get stabilized when they form hydrogen bonds with themselves in the bulk. And so, overall this is also entropically favorable. So, with this example we now are able to appreciate that host guest processes are always favorable and they are driven by increase in the entropy of the system, and these are also enthalpically favored. And now we will look at some examples related to appreciating the Chillet effect and macrocyclic effect. For example, let us consider a chemical reaction of copper 2 ion, aqueous medium with different ligands whose structure I will give below, and these experiments have been done at 25 degrees centigrade in water. The ligands are as follows: NH2 NH2, this is ethylene diamine, this is a open chain conformation, okay. This is a podend as we have discussed, and now we take the corresponding cyclic ligand as represented below. So, we have the three ligands, ligand 1, ligand 2, ligand 3. This particular ligand has got denticity 2, there are 2 binding sites, the 2 nitrogen atoms. This one has got 4 binding sites, this also has got 4 binding sites. The thermodynamic data has been provided, that is the enthalpy change in the standard state kilojoule per mole is minus 105 kilojoule per mole for the first complex, minus 90.4 for the second complex, and minus 76.6 for the third complex. The entropy contribution, the T delta S0 term in kilojoule per mole inverse has also been given: 7.1, 24.3, 64.0. And what we have to compute is the log K values, that is the binding constant which is obtained by the complexation of the copper ion with this particular ligands. So, we can see here that when copper ion now binds, so in this case we will have, in the first case we know that copper 2 plus ions form tetrahedral complexes, as well as they also form octahedral complexes. Okay. So, in this case the copper ion interacts. We have the copper ion here. We have the copper ion here. So, the copper ion essentially chelates with these particular ligands, and we can now calculate the log K values. So, we know that delta G0 is equal to delta H0 minus T delta S0. So, for the first one, minus 105 minus 7.1, that is 112.1 kilojoule per mole, and we know that delta G0 is equal to minus RT ln K, which is equal to minus 112.1, and we know that R is the universal gas constant 8.31, T is 298 Kelvin. So, we can now get the value of log K by dividing the natural logarithm, the value obtained from the natural logarithm, by 2.303. This will come out to be 112.1 into 10 to the power 3 by 298 into 8.31 into 2.303. This will be around 19.7. So, 19.7 is the log K value for the first complex. It is 20.1 if you calculate now for the other complex, and it is 24.8 for the third complex. So, it is very clear that the third complex is the most stable complex, because you can see, in addition to the chelate effect, so you have one chelate ring here, you have another chelate ring here, you have another chelate ring here, you have another chelate ring here, you also have a pre-organized, so you have the 4 chelate rings, plus you have a pre-organized host, which is having a very rigid and constrained geometry, and it also has the necessary converging sites. The nitrogen lone pair, as we have discussed, are oriented towards the copper ion to form this particular arrangement with the copper complexes with the 4 nitrogen atoms. Contrary to that, in case of the second ligand, we do have the chelate effect, which is operational, which is coming from the 3 different rings, and in the first case we only have the chelate effect, which is operational. So, the macrocyclic effect actually enhances the binding constant of the complex, and you can also see that the T delta S0 term is most favorable for the pre-organized host, as we realized that if the host is already pre-organized, then the entropy, unfavorable entropy loss does not take place, because conformational change is not necessary. However, in terms of the open chain conformation, for example, in this case the conformation has been drawn in a way so that it shows you the one which will be undergoing complexation, but you can also have the open chain conformation where the amino groups are far away from each other, and hence the necessary conformation has to be formed, and that is entropically unfavorable, and that is also reflected in the low value of T delta S0 compared to the value for the ligand 3. And for the ligand 1, obviously the T delta S0 term is the least, it is the least, and the enthalpy consideration wise, you can see delta H0 decreases because you are increasing the hydrophobic content in your molecule, you are increasing the number of carbon atoms. Therefore, the stabilization coming from hydrogen bonding is also reduced, number 1. Number 2, you are also decreasing the number of NH bonds when you are going from second to third. Okay, so when you go from second to third, you have replaced 2 of the NH bonds by the ethylene spacer, so overall, this hydrophobic hydrophilic balance is what decides delta H0, and a combination of both the enthalpy change and the entropy term is what decides the overall stability or the binding constant of these complexes. And now, to summarize this particular week's lecture, now we have seen a lot of aspects related to host guest design, and to complete this a series of lecture for the third week, the final topic which we would like to discuss in brief is about thermodynamic and kinetic selectivity. Thermodynamic and kinetic selectivity. Now, this is relevant because there are many processes in nature which do not happen at thermodynamic equilibrium. The processes are instantaneous, are fast, and many times there is a preference for one guest over the other. So, if you have, say for example, a mixture of metal ions, then you have a host which would specifically like to only bind with one metal ion and not the others. Similarly, you can have guest molecules, but you will have a host which is only sensitive to one guest molecule and not the others. For example, these kind of processes are very much relevant in nature. In case of enzymes, transport proteins, etc. And also, we know, for example, in case of hemoglobin in blood, it is supposed to take up only oxygen from a mixture of nitrogen, water, carbon dioxide, etc. So, it has very specific binding for oxygen out of a mixture of gases. So, in this case we need selectivity, and they, in this regard, both thermodynamic and kinetic selectivity are important. So, because hemoglobin needs to have very specific preference for oxygen, therefore, it should be able to bind to oxygen very strongly, and then once it binds, it should be able to transport oxygen to the site of interest, and there it should be able to release the oxygen wherever it is necessary. So, binding uptake process as well as release processes, both are very important in selectivity processes. Now, we define thermodynamic selectivity as the preference of one guest over the other. This is how we define thermodynamic selectivity, and we know that in general, when you have host plus guest, to give you the host guest complex, the K is the ratio of the concentration of the complex to that of the host and the guest, and the thermodynamic selectivity is essentially the ratio of this equilibrium constant of guest 1 in comparison to that of guest 2. So, larger is the value of this of the ratio of this ratio, more is going to be the thermodynamic selectivity of one guest over the other. That is simply reflected in the magnitude of the equilibrium constant being higher for guest 1 in comparison to that of guest 2, and you can play with the thermodynamic selectivity via the concept of lock and key principle we have discussed, pre-organization of the host and increasing the host guest interactions and increasing the host guest interactions, whereas kinetic selectivity are the processes which involve transport of guest at the fastest rate. So, when you have kinetic selectivity, it is the rate of the biochemical transformation or the rate of sensing and signaling that is most important. So, say you want to achieve a given biochemical transformation in the presence of a guest. So, you have a large enzyme or a large protein molecule that senses the guest, and then once it has sensed it, the transformation takes place and then the guest is released. Or you would like to transport say specifically one particular gas, so it has to sense it and then absorb it, and then it has to also transport it at the site of action. This involve rate processes, and kinetic selectivity does not need pre-organization. So pre-organization or rigidification of the host is not necessary for kinetic selectivity, because the enzyme undergoes rapid changes in conformation. It goes through a series of intermediate states where there are changes in conformation to accommodate the guest, and once it binds, it immediately transports and releases the guest at the site of action. And all these processes don't need pre-organization of the host. Rather, what it needs is reaching the transition state wherein the guest has got a pretty strained geometry and perform the rate and perform the process, complete the reaction, so that the desired selectivity or kinetic selectivity is achieved. So, this differentiates kinetic selectivity from thermodynamic selectivity. If you have a process where the binding is irreversible, very strong, the binding constant is high, kinetic selectivity will not be achieved, only thermodynamic selectivity will be achieved. But kinetic selectivity is something that is related to the rate of the process. Their binding is important, but the binding should not be very strong. It is the transport process and the subsequent release at the site of action which is of extreme relevance. So, kinetic and thermodynamic selectivity also plays a very important role in trying to understand, for example, supramolecular catalysis, understanding biological processes, and so on and so forth, and we will be discussing some of these things later on in the course as well. So, with this we complete this particular lecture. Thank you.